Hello, welcome to chapters 7 and 8. Chapter 7 was about random variables, and chapter 8 was about binomial and geometric distributions. First off, if we have a distribution of our random variable x, this is the bottom represents the probabilities that we get each of these values above. The one common thing is to find the mean and standard deviation. Now, the formula for the mean of that x is the sum of all x times their p-values. So I'm going to take that and move it back a little bit. So what we have to do is add up all the x times the p's. So 3 times 0.05 is 0.15, 5 times 0.15 is 0.75, 7 times 0.3 is 2.1, 9 times 0.2 is 1.8, and 11 times 0.3 is 3.3. If I add these all up, I get the value of 8.1. Now, my standard deviation of that distribution is the sum of all, oop, that's a terrible summation symbol, of x minus our mu. We're going to square that and then multiply it by our probability. Now, to do this, what I'll do is I'll take my x value, which is 3, subtract my mean, which is 8.1, square it. Now I multiply it by my probability, which is 0.05. Then I add that to this next one, which is 5 minus 8.1 squared times 0.15. Now you can see you can keep doing that until you get to your last one, 11 minus 8.1, square it, multiply it by 0.3. Plug those all in your calculator and you'll get a wonderful answer. And just a lot to write out. Now, to do this, what you do on a calculator, if you want a quicker way to do it, what I would do is put your values in L1 and L2. And then once they're in L1, L2, you hit stat, go over to one variable stats. Now here we have to put in L1, comma, L2 if it's a probability distribution like this. And when we hit enter, you can see that my x bar value is the same as we got up there. So that is our mean. And our standard deviation is down here, 2.406. They don't even give you the S of x, which is a sample standard deviation, because this is a theoretical situation. So they're not going to give you a sample standard deviation. All right. In a uniform distribution, keep in mind a uniform distribution is one that goes straight across. It goes from 0.4 all the way to 0.9. And if they don't tell you, a uniform distribution will go from 0 to 1. So from 0.4 to 0.9, that takes up half of the distribution. So this probability will be 0.5. Now there's some rules for means and rules for standard deviations or variances. The rules for means is if I apply a linear transformation to a data set, I can also apply that same linear transformation to the mean. Or if I am adding two data sets together, I can just add the mean of each of the data sets to equal the mean of both those data sets. Means are nice, they're really easy, they do what you want them to do. Standard deviations are not as fun because they're not as intuitive. Now, if I have a variance that I apply this linear transformation to the variance, the new variance is going to be b squared times the old variance. But if I square root both sides, my standard deviation of a plus bx is going to be just b times my old standard deviation, which is nice because a lot of times we're going to do standard deviation. You just have to know that that a does not affect your standard deviation. Now, if the two variables are independent, x and y, this is what I like to say is the Pythagorean theorem of statistics, because if you add the variables, you get sigma squared plus sigma squared equals the sigma of both of them squared, or even if you subtract the two variables, adding the variance will equal the variance of subtracting the variables. Most importantly, we see this with standard deviation. If I square root both sides, it's going to be the square root of sigma squared plus the square root of sigma y squared. That would be the sigma of both of them squared. And surprisingly, if you subtract the variables, you get the same exact standard deviation. Where I should have said, with the means, if you subtract the variables with the means, you subtract the variables with each individual mean. Now I'll do a problem that hopefully makes more sense. Suppose that x is normally distributed with this mean and the standard deviation, and y is normally distributed with a standard deviation of 6. Now, if I want to find the probability that x plus y, that's supposed to be an x, is greater than 95, first I need to find the mean of x plus y, and I need to find the standard deviation of x plus y. Well, since I know each individual standard deviation and each individual mean, I can just add the mean. 50 plus 30 is my new mean. However, my standard deviation, I have to use Pythagorean theorem. 8 squared plus 6 squared, square root, that's 64 plus 36 is 100. Square root of 100 is 10. Now I can solve the rest of the problem by breaking this down to z-scores, since I know the mean and standard deviation, and I know it's normally distributed, so I can find the probability from here. That's 15 over 10, which is 1.5. Then we take out our handy calculators and do a normal CDF from 1.5 to infinity, and we get a value of 3.8 times 10 to the negative 50. Now this doesn't look like a good answer, so hopefully you noticed what I did wrong. I wanted to put in 1.5, but I put in 15. So if I put in 1.5, hopefully this is a little bit more reasonable answer. 0.0668. So about 6-7% of the time, both these things will be above 6%, or be above 95 in value, whatever these things are. Now, if I want to find the probability x is greater than y, now this is hard to deal with because we're used to having some variable on this side. So what I like to do is subtract y from both sides, and what's probably x minus y is greater than 0. So your mean of x minus y and your standard deviation of x minus y, your mean is going to be mean of x minus mean of y, which is 20. The standard deviation is going to be 8 squared plus 6 squared square root, which again is 10. So this is the probability that my z-score is greater than 0 minus 20 over a standard deviation of 10, which is probably my z is greater than negative 2. Now this has got to be a pretty big probability because we're going to go from negative 2 all the way to a big number. So I'm going to guess before we even start that it's going to be big, but I didn't guess, so 0.977. All right. Here's another one. Maybe I'll set it up and and I won't carry out the whole calculation. Tom and George are in a golf tournament. Tom golfs with this distribution, George golfs with this distribution, and this means normal. That's your mean, that's your standard deviation. What is the probability that Tom gets a lower number to beat George? So Tom is lower than George. This is a pretty common question. Now we subtract George on both sides. You have to find the mean of Tom minus George, and you have to find the standard deviation of Tom minus George. So the mean of Tom minus George is 110 minus 100, which is 10. The standard deviation is going to be 10 squared plus 8 squared. square root it. So that's 164. We're looking at the square root of 164, 12.8. So that's to find the probability that my z-score is less than 0 minus 10 over 12.8. So that's negative 10 over 12.8. Probability the z-score is less than negative 0.78125. So I'm going to take a normal CDF from negative infinity all the way up to negative 0.78125, which is 0.217. So about 22% of the time, Tom is going to be George. Um, Even though George is the better golfer because he averages a smaller number. That makes sense now. Took me a second. All right, now we get to chapter 8. Chapter 8 has binomial settings and geometric settings. For a binomial setting, each the variable has to either have a success or failures. There's a fixed number of observations. This is a really big key to the binomial. Each observation is independent, and the probability of success is the same for each observation. Now, if a couple has 5 children, the mother has type O blood, the father has type A blood. There's a 25% chance each kid will end up with type O blood. What's the probability exactly 2 kids ends up with type O blood? That's this one right here. To do this, the probability that they get type O blood is 0.25. The probability that they don't or failure is 0.75. So if there's 5 kids, 2 of them have type O blood, 3 of them don't. Then we have to figure out how many times we can rearrange those, which is 5 choose 2. And this will give us the probability here. Now what we do on our calculator is, for the shortcut, we go to binomial PDF. And you type in how many values, so there's 5 kids. The probability of success is 0.25, and the number of successes we want in this case is 2. If we hit enter, you can see that about 26, there's about a 0.26 probability that 2 of the kids will have type O blood. Now, I could just hit second enter and modify this last number to a 3, and now I get my value over here. There's about a 0.087 chance that 3 kids have type O blood. And you can keep doing that to fill out the rest of the distribution. So this is the formula that they use for binomial probability. This NK, we usually write it N choose K like this, but this is another common form of writing it. Now a PDF will give the probability of that particular value, where a CDF is a cumulative distribution. So what it does is, if you have a distribution that looks like this for a PDF, your CDF takes this value and adds it to this value. So you start with the same value, but your next one adds this to the top of it, so it gets higher. Then you add the next one to the top of it, and it gets higher. And the next one gets higher, and so on, until finally you get to 100%. So that's the cumulative distribution. So if we do a CDF up until 2, it adds all the probabilities of getting 0, 1, and 2. Now, in a binomial situation, we can always find the mean by multiplying the n times the p, and the formula for the standard deviation is the square root of n times p times 1 minus p. And both of these are given on the AP test and on all my tests. To approximate a normal distribution, you have to check that n times p is greater than 10 and n times 1 minus p is greater than 10. And you can use the normal distribution if this gets messy. Our calculators are really nice where you could just use your binomial CDF, or you can do normal approximation. Both of them are good methods. Uh, and here's another example of binomial distribution. If Corrine makes 75% of her free throws, and each one's independent, find the probability she makes exactly 3 of those shots. To do it by hand, I would say 12 choose 3 is 0.75 to the third, 0.25. That means she failed 9 times. What I would do on a test is I would do a binomial PDF, 12, comma, 0.75, comma, 3. And you see the probability that she only makes 3 shots is 0.00003 something. Did I have that right? Oh, I should erase a 0. But it's a really low probability. Now we need to look at the geometric setting. The geometric setting, we have success and failure. Each observation is independent. The probability of success is the same for each observation, but this number 4 is different. What we're concerned about is the number of trials until we get our first success. The formula is always failure to the n minus 1 times the probability of success. So if I want to find the probability that takes, oh, there's no problem here. I should have one. So find the probability that you make your first shot on your 4th attempt, assuming that your probability of x is 0.75. We'll do the same example. So what this means is that person fails 3 times, and on the 4th time they get it right. So 0.25 to the third times 0.75. Another way to do it is do your geometric PDF. Your probability of success is 0.75, and you want to make it on the 4th time, comma 4. You get that? And it's 0.0117, I think. Yeah, 0.012, something like that. And that's the probability that they make their first shot on the 4th time. All right, and there's a shortcut that you don't have to use, but if they find the probability, what's the probability you make it on more than, say, 4 shots? You just take the probability of failure to that power. So if I took 0.25 to the 4th, 0.0039, there is a very small percentage chance, about a 0.3 percentage chance, that it would take more than 4 shots for her to make her first basket. All right, we're done with this long review. Hopefully it makes more sense to you.